An SPR drawdown only occurs under very specific circumstances.
The President of the United States has authority to release a full-scale drawdown, which means we release oil from our facilities at 4.4 million barrels a day. He also has the authority to do a limited drawdown, which allows the release of up to 30 million barrels of crude oil. The second person that is authorized to release oil from our facilities is the Secretary of Energy.
There have only been 2 drawdowns since the SPR was instituted. A drawdown was authorized after 2005's Hurricane Katrina. 140-mile-an-hour winds had torn through the Gulf Coast, damaging refineries and pipelines that feed the entire United States. And the SPR served the purpose for which it was intended: to ease the stresses of economic, geopolitical, and natural disasters.
We have to be ready when the President so decrees to go into full drawdown mode, in which we can supply the country with crude oil. And we have to be ready like almost the military in that regard.
The Strategic Petroleum Reserve may be the largest underground container in the world. But there are other containers that hold vast riches above ground. Silos.
We're standing on the 110-foot high silo, 60-foot diameter, and this is the one that holds a 250,000 bushel.
A silo's height means it can have a small footprint and still contain tremendous amounts of whatever needs storing, like grain, sand, or corn, to name but a few. Grain elevators and feed plants are comprised of multiple silos. Although a seemingly simple structure, a silo is actually a very complex edifice. At the Kroll family farm in Lebanon County, Pennsylvania, a construction crew from the Sollenberger Silos Corporation builds a new farm silo, utilizing the jump form method.
If you look at the forms, they're 4 foot high, and there's 3 4-foot forms on the concrete now. After they finish pouring the concrete in one form, the crewman will break the forms loose, and then they will push those out and jump them up to the next level. So that's why we call them jump forms.
Pouring the concrete involves precision and speed.
He moves the buggy continuously around so that the concrete fills the form level. He doesn't want to put it all in one place because it'll try to bulge the forms out. And so he fills it up even all the way around.
Steel rebar supports are placed in the concrete.
Engineers have designed these silos based on the material that's stored. If we store shell corn, there's a lot of horizontal pressure, and so we need more steel. That gives us the strength in the silo walls.
When completed, this farm silo will stand 92 feet high and contain 28,888 cubic feet of storage space. Today's silos are epic versions of their predecessors. Agricultural scientist Franklin Hiram King patented the first silo in 1889. King's silo was a modified barn, cylindrical in shape. He knew that the cylinder structure was strong and reduced the likelihood of spoilage. King's silo finally evolved into this behemoth, the largest farm silo in the United States. It stands 148 feet tall in Berks County, Pennsylvania.
In this big silo, there's over 90,000 cubic feet of storage capacity. And the Goodyear blimp has about 70,000 cubic feet, so this is bigger than a Goodyear blimp.
For most modern silos, concrete is king.
I always say concrete's for life. It takes very little maintenance, and you can put just about anything in it.
Silos in the SPR storage tanks are certainly impressive. But there's another small and humble container we use every day that's changed the course of our world: the metal can. One storage cavern in the U.S. Strategic Petroleum Reserve is large enough to contain the 1,450-foot Sears Tower, with room to spare. Containers will return on Modern Marvels, here on the History Channel. We now return to containers on Modern Marvels. The metal can, one of our most important containers. This seemingly simple device revolutionized the food and beverage industry. The shelves of grocery stores around the world and our own kitchen cabinets are filled with every conceivable shape and size.
It's so common that people don't realize how much work and effort goes into making a can. First of all, the speeds at which cans are made boggle people's minds pretty much.
For the last 125 years, Ball Corporation has been a leader in the food and beverage container industry. At their Golden, Colorado metal beverage plant, Ball creates billions of perfect cans.
Most can lines are designed to run around 2,000 a minute. We're making well over 100 million a day just in our plants. Each year, when you look at our industry, we're making 100 billion.
Production begins with 12,000-pound aluminum coils that unspool into a machine called a cupper.
The cupper creates this piece of product that is really the very first process of making a two-piece can. This process knocks out 12 of these at once, and these are then conveyed to a machine called the body maker.
The body maker drives a steel form into the cup, which extends the aluminum.
You can see here that it's untrimmed, it's a little rough on the top.
Before the can exits the body maker, the top is cut to its standard size, and a pressure dome is created.
Has the pressure dome here, which resists the carbonation from bulging it out. This can is then trimmed to have what we call a factory finish, so that every can has this nice trimmed height, and they're all exactly the same after this point.
Each can then journeys to a system of washers and dryers that produce clean containers ready for their next phase, the printer.
The printer is essentially the machine that paces the entire can line. It'll speed up or slow down, and the rest of the can line has to sort of behave in the same manner.
The printer uses up to 8 different colors of ink to design intricate labels. Then a fine lacquer covers the artwork. From here, the cans enter an oven that bakes on the ink and lacquer.
And then that can goes from that oven into what we call internal spray machines. And these spray the inside of the can with a coating, and then that is baked on as well. So you've got no metal exposure.
At each phase of the production line, the cans must be flawless, or else they're discarded and recycled. The final step prior to shipping is to create a neck and flange on the can.
We put a neck and a flange on the can. This neck and the flanging gives it a lot of strength, and it prepares it for the end, which comes on after the can is filled with product. An end comes on, and this flange is then rolled into what we call a double seam, which gives it a hermetic seal. Product is perfectly preserved from light or oxygen, and nothing comes out of the can either until you open it.
The cans are then aligned onto pallets, marked for transport, and sent to the warehouse to await delivery. But making food and beverage containers hasn't always been this fast or streamlined. The sterile container can be traced back to an 18th century French general, Napoleon Bonaparte.
In 1795, as he was trying to conquer Europe, he was having a very difficult time obtaining the necessary foodstuffs for his armies. And he went back to the French government, and they actually started a contest to develop a feeding system that would make food non-perishable. And a fellow by the name of